Welcome to the video lecture on inverse trigonometric functions. First, let's recall a few facts about inverse functions. Remember that f is a one-to-one function with domain A and range B. Then, this notation means f inverse is the inverse function with domain B and range A. In other words, the inverse function swaps the x's and it swaps the y's. The definition of being one-to-one means that for every x, there is exactly one and only one y. We say that a function is one-to-one if it passes the vertical line test. That's going to show that it's actually a function to begin with. And if it passes the horizontal line test, then that means it's one-to-one and will have an inverse function. So let's think about the sine function. Is it considered a one-to-one function? Does it have, for every x, exactly one and only one y value? And a quick, easy way to see whether or not it's one-to-one is just to look at the graph of the sine curve. And you should know by now what that looks like. It's periodic, so it's going to keep going in both directions, something like this. Does this pass the vertical line test? Yes, because the sine curve is a function. Does it pass the horizontal line test? No. All of these places, it intersects those horizontal lines in more than one point. So it has y values that are repeating over and over and over again because it's periodic. So for that reason, the sine is not a one-to-one function, which means it shouldn't have an inverse function. But we can create an inverse sine function to exist if we restrict the domain of the sine curve in such a way so that the portion of the function that we're looking at is one-to-one. So let's think about how we could do that. What we want to do is take a piece of the sine curve, a piece of the graph that's representative of the sine curve so that it's going through all the all the y values that the sine curve normally would go through, but doing so in such a way that it will still pass that horizontal line test. And there's many ways that you could decide to do this, but what the convention is to take just the piece of the sine curve between negative pi over 2 and pi over 2. So that's going to hit the negative at -1, hit the minimum of the sine curve at -1, and it's also going to hit the maximum of the sine curve at +1. So you get this little piece of the sine curve that looks like this. This does pass the horizontal line test. So therefore, it does have an inverse. So this is the graph of sine of x, but it's on the domain minus pi over 2 up to pi over 2, and the range here is -1 to 1. So the convention is to restrict it to this particular domain so that the sine function attains all of its range values, -1 to 1, but it's hitting them only once. It's hitting everything between -1 and 1 exactly once so that it ensures that it will pass that horizontal line test and therefore have an inverse. Okay, so here's what the graphs would look like drawn a little bit better. Here's your sine curve, and then over here, this is sine of x, and over here, this curve is also sine of x. It has that sort of S shape, and this is between minus pi over 2 and pi over 2, which is about 1.5. This dashed curve is what the inverse sine function is going to look like. And remember that a function and its inverse should be reflections across the line y equals x. So these two graphs are. Here's how we're going to define this inverse function. We're going to say that the inverse sine function is the function sine with this little -1, that's notation for inverse, with the domain -1 to 1 and range minus pi over 2 to pi over 2. So recall up here, when I say that the sine function has domain minus pi over 2 to pi over 2 and range -1 to 1, then that means the inverse sine function is going to swap those. They swap domain and range. So the domain will become -1 to 1 on the inverse function, and the range will become -π/2 to π/2. And what the inverse sine function is doing is it's telling us angles. That's what all these range values are. These are the angles that if you were to take the sine of them would give you back these domain values here. Okay? We'll practice using this, but it's a little bit tricky at first. So the domain of the inverse sine function is -1 to 1, and the range of the inverse sine function is -π/2 to π/2. So what I want you to remember, and this is very, very important, is that the inverse sine function finds angles just in this range, -π/2 to π/2. And think about what range that is. That's quadrant 1 for those positive angles and quadrant 4 for those negative angles. So you're only going to be giving me angles that are either quadrant 1 or quadrant 4 angles within the interval -π/2 to π/2. Now because an inverse function and the original function sort of undo each other, we get a couple of these cancellation properties down here. So if you were to first take the inverse sine of x, where x is between -1 and 1, and then take the sine of that value, they should cancel each other out and give you back the original x. So it's sort of like these two things cancel each other out. If you start with an angle between -π/2 and π/2, and you take the sine of it, then the inverse sine of that should, again, cancel it out and give you back that original angle x. Okay, so let's practice using this inverse sine function a little bit. If the question says, find the inverse sine of 1/2, the way you're probably going to want to think about this is by thinking backwards. This really means what angle, I'll call it theta, makes sine of theta equal to this original number 1/2. So you're thinking in reverse. Inverse sines find angles. So what angle gives you the sine of that angle equaling 1/2? And 1/2 is one of those nice numbers that we see on our unit circle quite often. So if you think about your unit circle here for a moment, 1/2 shows up, and sine is the y coordinate. 1/2 shows up as the y coordinate for the angle π/6. So that's the angle that we're looking for here. So what angle theta do I need so that the sine of it is equal to 1/2? If we have an angle of theta equaling π/6, then that would work. Now your question might be, well, why couldn't I let theta be 5π/6? Because that also has a y coordinate of 1/2 as well. And the reason we're not going to give 5π/6 as our answer is because the angles that you give for these answers always have to lie in the range -π/2 to π/2. In other words, quadrant 1 or quadrant 4. And 5π/6 is a quadrant 2 angle. So you only want to give the value of the angle that's either in quadrant 1 or quadrant 4. Okay? So let's think about this one. Inverse sine of -1/2. That's the same thing as saying what angle theta, if you were to take the sine of it, would give you back -1/2. So if you think about your unit circle again, there's lots of values here where the y coordinate is a -1/2. You could give 11π/6, you could give 7π/6, but neither one of those angles, 7π/6 or 11π/6, is between -π/2 and π/2. 11π/6 is a quadrant 4 angle, but it's not between 0 and -π/2. So all we have to do is realize that we want a π/6 angle, but we want it in quadrant 4, and we want it to be within -π/2 to π/2, so it's got to be -π/6. In other words, it's got to be going clockwise right here to give you that -1/2 sine value. So anytime you're using an inverse sine function, make sure that the angle that you give for theta has to be between minus pi over 2 and positive pi over 2. All right, let's try inverse sine of 3/2. So in order to figure this out, this would be like saying, okay, sine of what angle theta would give me back 3/2? Well, 3/2 is 1.5. Think about your unit circle. What's the largest value that sine ever takes on? The largest that sine ever gets is 1, and 1.5 is obviously bigger than 1. So there's no angle that's ever going to make sine become 1.5 because it can't ever get that high. So this has no solution. Okay? The last one here says the inverse sine of 1/3. So this is like saying sine of what angle theta is going to give you 1/3. Now that's not one of these fractions that we typically see on our unit circle. So this is not going to end up being one of our nice angles. So the only way to figure this out would be to use our calculator, and you would type this expression in exactly as is on your calculator. And then you want to use whatever mode would be appropriate. So typically I tend to stick with radians most of the time unless I'm doing word problems that happen to have degrees involved. So let's pull up the calculator. Let's check our mode. I'm still in degree mode, so I'm going to switch it to radian, and then we're just going to type in inverse sine of 1/3. And the answer that I'm getting here is in radians. So this is an angle. Inverse sine is always giving us an angle, and this would be about 0.34 radians. Okay? All right, let's try some more. Now these are going to start to get a little bit trickier. So here we want to find the inverse sine of pi over 6. So let's think about this. Inverse sine of sine. You're trying to take an inverse function of its original function. So there's a cancellation that should be going on here. However, inverse sine does have this restricted range here. You have to always be working within minus pi over 2 to pi over 2 for your angles. And luckily for us, pi over 6 is in this range, minus pi over 2 to pi over 2. So we can use that cancellation law, cancel these guys out, and we will get pi over 6 right back again. But if I go to the next problem, again, we're trying to do an inverse sine of a sine. So they do really want to cancel each other out. However, the original angle that we're starting with, 7 pi over 6, is not in minus pi over 2 to pi over 2. So we can't just cancel these guys out right away and give 7 pi over 6 as our answer. We're going to have to do a little bit more work than that. So here's what we do. We just start working the problem from the inside out. What is the sine of 7 pi over 6? So think about your unit circle. Here's 7 pi over 6. The sine would be the y, so that's negative 1/2. So this is going to be negative 1/2. Now you need to think about what angle, if you were to take the sine of it, would give you negative 1/2 back. Well, we know it's a pi over 6 angle, we just need to know which one it is. And we want it to be an angle that's either in quadrant 1 or down here in quadrant 4. Well, it can't be a quadrant 1 angle because sine is always positive in quadrant 1, and we want it to be a negative 1/2. So it's got to be an angle down here. And what angle down here between 0 and negative pi over 2 is going to give us a y value that's negative 1/2? It's got to be negative pi over 6. So this angle down here, the pi over 6 angle that's in the 4th quadrant going clockwise. So notice we didn't get back exactly what we started with. We got back an equivalent angle, but not exactly the same angle. So let's do that again over here. We want to be able to just cancel these guys out, but 11 pi over 6 is not in minus pi over 2 to pi over 2. So what we're going to do is we're going to work from the inside out, and we're going to think about what's the sine of 11 pi over 6. So 11 pi over 6 is over here. Its y value is negative 1/2. So we replace that with negative 1/2. And what angle between minus pi over 2 and pi over 2 has the sine of it equaling negative 1/2? Well, it's got to be a pi over 6 angle to get that 1/2, and it's got to be negative so that we're down here in quadrant 4. So we got the same answer as the last problem, even though the angle that we started with was a little bit different. Okay? On the next two here, again, it's wanting to cancel out. Notice the order is switched. This time we're doing the inverse sine first and then taking the sine of it. Now on this one, what you want right here, since this is doing an inverse sine first instead of the sine first, you need this quantity right here to be between negative 1 and 1 in order for this to exist. If this number was bigger than 1, then it would be kind of like this last example up here where we were trying to find a value of sine that's bigger than 1, which can never happen. So you just need to make sure that this input right here is between negative 1 and 1, which this is. So it should cancel right out to just a 1/2. But let's see why. Okay? What angle, if you were to take the sine of it, would give you positive 1/2? Well, that's that pi over 6 angle again, and I'd want the positive pi over 6 because I want a positive 1/2. So if I replace inverse sine of 1/2 with pi over 6, and then I take the sine of that, that's going to give me right back again to that 1/2. So that's why they cancel each other out. On this one, it's not going to be so nice to do by hand because 3/4 isn't one of those nice y values on our unit circle. But we don't need to do anything tricky here. Since this input is between negative 1 and 1, we know that this is going to exist, so these should automatically cancel each other out, and this will just be 3/4. I don't have to do any work. Now these next two are going to get a little bit more complicated because now I'm not doing a sine and an inverse sine, so they would cancel out automatically. Here I'm taking a cosine of an inverse sine. So they aren't necessarily going to cancel each other out. Something different is going on. So here's how you would want to do these. Here's the best strategy. Let's call this quantity here. Remember, inverse sine finds you an angle. So let's call this whole thing theta. Okay? So I'm going to erase that and rewrite that down here as saying theta is this inverse sine of 2/7. I am going to call this whole thing in parentheses theta. Now if you think about that, this is really saying theta is inverse sine of 2/7, which really means sine of theta is equal to 2/7. So sine of that angle theta is 2/7. Now if you know what the sine of an angle is, how can you figure out what the cosine of that angle is? So I'm replacing all of this with theta, so now it's really turning into the problem, okay, what's cosine of theta then? That's what we're trying to find. So if I know what sine is, how can I find its cosine value? We do that with triangles. We draw a right triangle, doesn't matter how you draw it. Call that acute angle at the bottom theta. Sine is opposite over hypotenuse. So I'm going to call the opposite side 2. I'm going to call the hypotenuse 7. 7 squared is 49. 49 minus 2 squared, or 4, would be 45. And square root of 45 is square root of 9 times square root of 7. So it reduces, square root of 9 times square root of 5. So it reduces to 3 root 5. So that's this missing side right here. So now I know all 3 sides of my triangle. So if sine of theta is 2/7, and that gives me this little triangle, then what would cosine of theta become? Well, cosine of theta is adjacent over hypotenuse. So this is 3 root 5 all over 7. And we're done because we are in quadrant 1 since this 2/7 was a positive sine value, and in quadrant 1 cosine is also positive. Okay, let's try that process again on this one. So inverse sine of negative 3/4. Now remember, an inverse sine is finding you an angle. So we're going to want to call all of this an angle. And really we're trying to think of this problem as saying, okay, what is tangent of theta? Well, how are we going to figure out tangent of theta? Well, we need to draw a triangle using this information here. We're going to let theta be the inverse sine of negative 3/4. So therefore, the sine of theta should equal that negative 3/4. Sine is opposite over hypotenuse. So let's draw a triangle. Opposite side would be the 3, hypotenuse would be the 4. I'm ignoring the negative for a moment. We'll get to that in a moment, but let's just draw the sides of our triangle first. Square of 4 is 16. Square of 3 is 9. So 16 minus 9 would be 7. So this side over here needs to be square root of 7 by Pythagorean theorem. What we wanted to know from this triangle is what tangent of theta was. So what should tangent of theta be? Tangent of theta is opposite over adjacent. So 3 over root 7. Now we need to think about quadrants here for a moment. Okay? This original sine of theta was negative 3/4. So when we find inverse sine of negative 3/4, remember, inverse sine only gives angles either in quadrant 1 if this number is positive, or quadrant 4 if this number is negative. So we need theta to be either in quadrant 1 or quadrant 4. Well, since this is a negative 3/4, that means theta needs to be in quadrant 4. So what sine is tangent in quadrant 4? Well, tangent is negative in quadrant 4. So our answer shouldn't be 3 over root 7, it should be negative 3 over root 7. And if you want to rationalize the denominator, you certainly can. Okay? Now that we've talked about sine, let's do a similar process for cosine. So now we're going to talk about the inverse cosine function. Is the cosine function 1-to-1? Well, here's the graph of the cosine of x, that nice U shape, and because it's periodic, it's not going to be 1-to-1 because it won't pass that horizontal line test. So here's the convention, and there's more than one way to do this, but this is how it's been decided that we're going to do this. We're going to take the piece of the graph from 0 to pi. So we're going to take just the part of the graph from here down to here. That way cosine is hitting everything between -1 and 1. You want to make sure that it's hitting all those y values exactly once. And then what we're going to do is we're going to take the inverse by swapping that domain in that range. So what we're going to say is the inverse cosine function will now have domain -1-1 and range 0 to pi. And we're going to say that the inverse cosine of x is equal to y if and only if cosine of y gives you back x. So what you want to keep in mind this time around is it's a slightly different range of values. The domain of inverse cosine is -1-1, and the range is 0 to pi. So think about the picture there. 0 to pi is all of the angles in quadrant 1 and all of these angles in quadrant 2. So now the kind of angles that you're going to be getting for answers when you do an inverse cosine should just be angles in quadrant 1 if you're talking about a positive input, or an angle in quadrant 2 if you're talking about a negative input. And we do have those cancellation rules again. Cosine of inverse cosine of x will give you back x as long as the x is between -1 and 1. And the inverse cosine of cosine of x will give you back x as long as x is between 0 and pi. So let's try some examples here. What would be the inverse cosine of a half? In other words, cosine of what angle theta would give us back 1/2? We're looking for this theta. And the theta that we give for our answer has to lie between 0 and pi. So if it's positive, it's got to be in quadrant 1, and if it's negative, it's got to be the angle that's in quadrant 2. So we're only allowed to give theta in between this range 0 to pi. So which angle between 0 and pi has the cosine equaling 1/2. You think about your unit circle, cosines are x's. Here's positive 1/2 right here. All of these x's over here would be negatives. So we don't want anything in quadrant 2. We want this one right here, which is pi over 3. So our answer is pi over 3. The angle that we're looking for is pi over 3. All right, now we want inverse cosine of negative 1/2. So what angle is this? This is some theta. And cosine of that theta is supposed to be giving us negative 1/2. So if we pull up our unit circle again, since we want a negative, we need to be in quadrant 2, and negative 1/2 shows up right here, and that's when the angle is 2 pi over 3. So now we're giving 2 pi over 3, a quadrant 2 angle, as our answer. When does what is the inverse cosine of 3/2? Well, it's some angle, and the cosine of that angle is supposed to equal 3/2. But that is impossible because 3/2 is bigger than 1, and cosine never gets bigger than 1. Its maximum is positive 1, so this is impossible. Okay? Let's try inverse cosine of a third. This is going to be some angle theta, and cosine of that angle is supposed to give us 1/3 back. Well, 1/3 is not one of these nice angles on our unit circle, so this is something you would have to do on your calculator. So let's pull it up, and we would just do inverse cosine of 1/3. And remember, we're in radian mode here, so 1.23 radians would be our angle. All right, let's try some trickier ones. Inverse cosine of pi over 6. So first of all, try to use your shortcuts if you can. This is a cosine inverse of a cosine, so they really want to cancel each other out. All you need to make sure of is that this angle that you're starting with here, it needs to be between 0 and pi. If it is, then they will cancel out, and pi over 6 is between 0 and pi. So this is just going to be pi over 6. If I look at the next one, again, I want to do an inverse cosine of 5 pi over 4. Is 5 pi over 4 between 0 and pi? Well, think about your unit circle again. 5 pi over 4 is down here in quadrant 3. So it's not between quadrant 1 and quadrant 2. So this isn't going to cancel out exactly like we would like. We're not just going to get 5 pi over 4 back. So the only way to do this is to work from the inside out. Cosine of 5 pi over 4, it's a pi over 4 angle, so that's a root 2 over 2, but that was quadrant 3, remember? So that's a negative. Which angle between 0 and pi, in other words, between quadrant 1 and quadrant 2, has as its cosine value negative root 2 over 2? It would be the angle in quadrant 2, because that's how we get negatives, and it would have to be right here, and that's the angle 3 pi over 4. So the only angle we're allowed to give for our answer is 3 pi over 4, because that's the only angle within this range, 0 to pi, that has negative cosine value equal to negative root 2 over 2. Okay, the next one here, again, it really wants to cancel out, but this is not between 0 and pi. 11 pi over 6 is down there in quadrant 4. So in order to figure this out, we think about cosine. It's a pi over 6, so that's a root 3 over 2, and in quadrant 4, that's positive. So now, which angle between 0 and pi has a cosine value of root 3 over 2? There's only one that's positive, and that's positive pi over 6. So that would be this angle right here. This is the only one that's going to give you a positive square root of 3 over 2 if you're restricted to 0 to pi, like we are. Okay, the next two, now we're also doing cosine of cosine inverse. We've just switched the order a little bit. And as long as this number here is between negative 1 and 1, this should exist and these should cancel out. So this is just going to be a 1/2. And 3/4 is also between negative 1 and 1, so this angle does exist. It's not a nice angle that we know of by hand, but it does exist, and these should cancel out, giving me just 3/4. Okay, getting into some trickier ones now. Notice this, next one. This is a hard one. We have cosine of inverse cosine of 2/7 plus inverse sine of -3/4. Now, in order to do this problem, remember that inverse cosines and inverse sines are angles. So this is all an angle. Let's call it alpha. And this is all an angle. Let's call it beta. So this is really asking for what is cosine of alpha plus beta. Now remember, you're not allowed to figure that out by just doing cosine of alpha and cosine of beta. This requires that sum formula identity that we have for cosine, which is cosine of the first angle times cosine of the second angle minus sine of the first angle, sine of the second angle. And what I'm going to do next here is substitute in what all these alphas and betas are going to be based on some triangles. So doing a little scratch work down here, if we let our alpha be this inverse cosine of 2/7, what that really means is cosine of alpha must be equal to 2/7. And that means we can draw a triangle. Here's alpha. Cosine is adjacent over hypotenuse. So this could be 2, and this would be 7. 49 minus 4 is 45, and the square root of 45 reduces to 3√5. So there's my triangle. So what would the cosine of alpha be according to this triangle? Well, we already knew that. That was 2/7. What's the sine of alpha on this triangle? Well, according to this triangle, sine is opposite over hypotenuse, so that would be 3√5 over 7. I'm just filling in the cosine alpha and the sine alpha for now. Next, we'll do something similar for the betas. Now, let's just do a quick check. 2/7 was positive, so we're talking about quadrant 1. Alpha here has to be in quadrant 1 because we're only allowed for inverse cosines to be in quadrants 1 or quadrants 2. And if the value here is positive, that forces us to be quadrant 1. So sine and cosine are both positive in quadrant 1. Okay, now let's do this all over again, but this time we're going to do it for this beta angle. So we're going to let beta be inverse sine of -3/4, which means that sine of beta is supposed to equal -3/4. So let's draw a triangle. Beta's down here in the corner. Sine is opposite over hypotenuse. So this is 3 and this is 4. I'm ignoring the sine for a moment. Let's find the missing side here. 16 minus 9 is 7, so this would be square root of 7. So what would cosine of beta be on this triangle? Well, cosine is adjacent over hypotenuse, so √7 over 4. And sine is opposite over hypotenuse, so that was that 3/4. But here's where we need to worry about our quadrants and our sines. Because sine of beta was -3/4, and in inverse sines, you're allowed to only be between 0 and pi over 2 or -pi over 2 and 0, quadrants 1 or quadrants 4. Since this is negative, that means we're down here. We're in quadrant 4 for beta. So in quadrant 4, sine is negative, but cosine is positive. So that's how I figure out my sines. All we have to do now, since we know these 4 pieces, is just go ahead and simplify. So let's just do a little bit of algebra. When I multiply here, I get 2√7 over 28. Minus times a minus becomes a plus. 3√5 times 3 is 9√5 over 28. And you could leave it like that if you wanted to make it all over a single 28 and do 2√7 plus 9√5. That's fine too. Either way is acceptable. Okay? Alright, so that one's probably about as hard as they get, right, using that sum formula. Let's try the next example here. This one's a little bit simpler because I only have the one inverse cosine showing up, Remember, this is going to be an angle, so if we call all of this theta, this is really asking us for what is tangent of theta. And if we're letting theta be this inverse cosine of -3/4, that's saying that cosine of theta is equal to -3/4. Let's draw a triangle. Here's my theta. Cosine is adjacent over hypotenuse. So the 3 is the adjacent side, the 4 is the hypotenuse. 16 minus 9 is 7, so there's that √7. And what quadrant are we in? For cosines, your angle is either quadrant 1 or quadrant 2. And if this is a -3/4, that means theta has to be in quadrant 2. Okay? So now, what are we looking for here? We drew this triangle so we could figure out what? We drew it so we could figure out what tangent of theta is. So according to this triangle, tangent of theta is opposite over hypotenuse, so √7/3. And if we're in quadrant 2, is tangent positive or negative in quadrant 2? It's negative. So our answer needs to be negative √7/3. Okay, next one is similar but a little bit different because there's no actual numbers here. There's no fractions like 3/4 or whatever. You have an x involved, but we're going to do it exactly the same way. Whenever you see an inverse trig function, like right here, that's your angle. So let's call it theta. So what this is really asking us to find is sine of 2 theta. And we're letting theta be this inverse cosine of x, which means cosine of theta is equal to x. And normally what we would do at this point is we would draw a triangle. Our angle is this theta, and if cosine is adjacent over hypotenuse, that's what this x needs to be. So I'm going to make this an x over a 1, and I'm going to let the adjacent side be the x, the hypotenuse side be 1, and look at what the Pythagorean theorem is going to tell me. This side needs to be that hypotenuse squared, which is 1, minus the adjacent side squared, so x squared. So there's my 3 sides. What I want to do next here is figure out sine of 2 theta. Now, unfortunately, this triangle is for theta, not for 2 theta. So I can't just do opposite over hypotenuse here. That would be incorrect, because that's what sine of theta is. That's not what sine of 2 theta is. So how am I going to figure out what sine of 2 theta is? That's where those identities come into play. We have to turn this into something using just a theta, and that's where that double angle identity comes into play. Sine of 2 theta is 2 sine of theta cosine of theta. So now I've changed these angles to thetas, which is good because I know what those are from this triangle over here. So according to my triangle, what would sine of theta be? Opposite over hypotenuse. So square root of 1 minus x squared all over 1. And what is cosine of theta on this triangle? It's adjacent over hypotenuse, so x over 1, or just x. And if we just rewrite it by squeezing that x in between the 2 and the radical to make it look a little bit cleaner, here would be our answer. Okay, we've talked about the inverse sine function, we've talked about the inverse cosine function, now let's talk about the inverse tangent function. So here's the graph of tangent of x. Again, it's not going to pass that horizontal line test because of its periodic nature. So in order to make this have an inverse, we're going to need to restrict the domain. And the choice that's made here is to restrict it so that we look at it just between minus pi over 2 and pi over 2. So between those two asymptotes on either side. So we're going to look at it between minus pi over 2 and pi over 2. Not including those endpoints because those are asymptotes. So what we're going to say is that the inverse tangent function is going to have a domain of minus infinity to infinity and a range of minus pi over 2 to positive pi over 2. And the reason for that is on this piece of the graph, for tangent of x, if we look at just this one between minus pi over 2 and pi over 2, look at its range. It shoots all the way down and all the way up. So this little piece of the graph goes from minus pi over 2 to pi over 2 for x and minus infinity to infinity for the y's. In the inverse, we're going to switch that. We swap x's and y's. So the domain becomes this minus infinity to infinity, and the range becomes that minus pi over 2 to pi over 2, which is, on a picture, quadrant 1 and quadrant 4 again, just like sine. Okay, so inverse tangent and inverse sine have almost identical restrictions. The only difference would be for inverse tangent, you're not allowed to actually hit those endpoints at pi over 2 or minus pi over 2. So inverse tangent of x will equal to y if and only if tangent of y is equal to x. If this x is any real number, then you can automatically cancel out the tangent and the inverse tangent and get x right back again. And if x is an angle between minus pi over 2 and pi over 2, then you can cancel these out and get just x again. So let's practice. Inverse tangent of root 3 over 3. So call this theta, if you will. And this is like saying tangent of what angle theta will give us back root 3 over 3. Think about your unit circle here. Tangents are y's over x's. So if I were to divide a y over an x, which one of these is going to end up being a root 3 over 3? And it turns out it has to be this pi over 6 right here. And I'll show you why. That's got a y of a 1/2 and an x of a root 3 over 2. So if we did sine of theta over cosine of theta, and if we looked at that pi over 6, remember that sine of pi over 6 was 1/2, and cosine of pi over 6 was root 3 over 2. The 2's cancel. You get 1 over root 3, and when you rationalize that denominator, that's what gives you that root 3 over 3. So the angle that we're looking for here is pi over 6, and it needs to be that quadrant 1 pi over 6, because here our theta has to be between minus pi over 2 and pi over 2. So in this region here or this region here, quadrants 1 or 4. So which angle is going to give us negative root 3 over 3 when we take the tangent of it? Well, it's going to be a pi over 6 again, but this time it's got to be the one down here in quadrant 4. And we don't want 11 pi over 6. We want the angle equivalent to it that's in this range. So we're looking for that minus pi over 6, the angle going clockwise down into quadrant 4. Okay, on this one, this would be like saying tangent of what angle theta is equal to 3/2. And when we did these for sines and cosines, we said that this didn't exist because sine and cosines have maximum values of 1, and 3/2 is bigger than 1. But think about the graph of tangent up here. It doesn't have a max or a min. It goes all the way up to infinity and all the way down to minus infinity. So it does hit 3/2 at some value. It's not a value that we know by heart because it's not on our unit circle, but it does exist. So this will have a value, and the only way to figure it out is to use your calculator. So you would just do inverse tangent of 3/2. And this is in radians, so 0.98 radians. And similarly for this, inverse tangent of 1/3, this is like saying tangent of what angle would give me back 1/3. It's not one I know because it's not going to be a nice value from my unit circle, so I have to use my calculator. So inverse tangent of 1/3, whoops, too many parentheses, and we get 0.32 radians. Alright, let's look at some of the trickier ones here again. We want inverse tangent of pi over 6. So as long as this angle right here is in our restricted range, minus pi over 2 to pi over 2, then we're good, and we will get cancellation between a tangent and an inverse tangent. So this is going to work and cancel right out because pi over 6 is right in that quadrant 1. So we're good here. But when we get to 5 pi over 6, that's in quadrant 2, so that's not going to be in minus pi over 2 to pi over 2. So we're not going to get that nice cancellation, so we have to work from the inside out. Remember, tangents are sines over cosines. So if we think about our unit circle, here's 5 pi over 6. The sine is 1/2, and the cosine is negative root 3 over 2. So I would need a 1/2 on top and a negative root 3 over 2 on the bottom, so those 2's are going to cancel out. So this is negative 1 over root 3, or if you rationalize your denominator, negative root 3 over 3. So what angle is going to give me that same fraction back that's in this range right here? Well, it's a pi over 6, obviously, because that's what we use to get this negative root 3 over 3. But we need the pi over 6 angle that's in here, in quadrant 4, because we want it to be negative. So it's got to be negative pi over 6, because that's the angle in quadrant 4 that also lies within this range. Okay, this one here, again, 11 pi over 6 is not between minus pi over 2 and pi over 2, so we're going to need to work from the outside in. 11 pi over 6 is in a quadrant 4 over here, and we want this y over this x. So this would be negative 1/2 for the y, root 3 over 2 for the x, so it's that inverse tangent of negative 1 over root 3 again, just like these other problems. So we know this is a pi over 6 angle, but because it's negative, I want the equivalent angle of a pi over 6, but in quadrant 4, lying between negative pi over 2 and pi over 2. So it's that negative pi over 6 again. So these are the same final answer, even though we started with different inputs. And then these next two, we're doing another cancellation of a tangent and an inverse tangent. As long as this number is any real number, remember, now we're not restricted to negative 1 to 1. Here we're using all reals because tangent goes all the way up and all the way down. So as long as this is any real number, these will cancel out, and you don't have to do any work at all. Okay? All right, next one. Here's that inverse cosine. Remember, that's an angle. Anytime you see that inverse symbol, then you know you're talking about an angle. So this is some theta, and we're looking for tangent of theta. So we're going to let theta be inverse cosine of 2/7, which means cosine of theta is equal to 2/7. Draw a triangle. Here's your theta. Cosine is adjacent over hypotenuse. 49 minus 4 is 45. Square root of 45 is that 3 root 5. So what would the tangent of this theta be? It would be opposite over adjacent. But we have to worry about quadrants. Inverse cosine, remember, that was the inverse trig function that was being referred to here. So you have to think about inverse cosine's restrictions. Inverse cosine is quadrant 1 and quadrant 2, between 0 and pi. And if theta is giving us the cosine value equaling a positive 2/7, then that means we're right here in quadrant 1. And in quadrant 1, tangent is also positive. So our final answer, positive 3 root 5 over 2. All right, the next one here is another tough one, because I have two inverse symbols showing up. Each one of these is an angle. So let's call this alpha, and let's call this beta. So this is really asking us to find tangent of alpha plus beta. And you can't just do tangent of the alpha plus the tangent of the beta. It doesn't distribute like that. You have to use the sum identity for tangent, and this should be memorized. And that identity is tangent of the first plus tangent of the second, over 1 minus tangent of the first times tangent of the second. So we're going to need to figure out what tangent of alpha is and tangent of beta is, and then I'm going to substitute those values into this formula. So how do we find tangent of alpha and tangent of beta? We go back to how we defined alpha and beta. So first we let alpha be inverse tangent of negative 3/4. So that means tangent of alpha is equal to negative 3/4. Now normally at this point we would go and construct a triangle, and then we could figure out cosine, sines, blah blah blah. But remember what we needed for our formula up here. All we needed to know was tangent of alpha, right here and right here. And that's what this negative 3/4 is. So don't create extra work for yourself. This is going to be a negative 3/4 that I substitute in here. And this is going to be a negative 3/4 that I substitute in here. Still need to figure out what this one is and this one, but then I'll have my answer. So you don't even need to make a triangle for this one because you already know what tangent of alpha is directly. Alright, let's go ahead and do the beta angle. So let's let beta be inverse cosine of 2/3, which means cosine of beta is equal to positive 2/3. Draw a triangle. Cosine is adjacent over hypotenuse. Whoops, 3. So the missing side would be 9 minus 4, which is 5, and I need the square root of that. So if I want the tangent of beta, according to this triangle, that would be opposite over adjacent, so root 5 over 2. And what quadrant are we in? Well, if we want an inverse cosine of a positive, remember, here's inverse cosine and how it's defined. And if it's a positive angle, then you have to be quadrant 1. So this is quadrant 1, and tangent of that beta in quadrant 1 would also be positive. So I'm going to use a root 5 over 2 here and here. Alright, now we need to figure out what that is. So let's go ahead and see if we can simplify here. We're going to get negative 3/4 plus root 5 over 2 all over 1. Minus minus becomes plus, and on top we're going to get 3 root 5 all over 8. Now this is fractions within fractions, so I would want to simplify here a little bit, and I could do that by multiplying by 8, the common denominator, on top and bottom. Negative 3/4 times 8. Well, 4 goes into 8 twice, so that 2 times this negative 3 is going to give me negative 6. And then 2 goes into 8 4 times, so that's going to give me a 4 root 5 on top. On the bottom, 1 times 8 is 8, and here the 8's cancel, just giving me 3 root 5. And for me, it's fine if you leave it like that. If you were asked to rationalize the denominator, you would need to multiply by a conjugate. Okay, next one. Sine of 2 inverse tangent of x. So this is just like the other ones, except we don't have fractions here. We have an x. Don't let that throw you. Anytime you see an inverse symbol like this, that's an angle, so call it theta. So this is really asking us to find sine of 2 theta, and we're letting theta be the inverse tangent of x, which means tangent of theta is equal to that x. And we're going to draw a triangle. The angle is this theta right here, and tangent is supposed to be opposite over adjacent, and that means I'm going to have to put this over 1 and make this x over 1. So my hypotenuse would be square root of the 2 legs squared and added. So this would have to be the x squared plus 1 squared, which is just 1. Alright, so I have my triangle. Now what do we want to know from it? We want to know sine of 2 theta, which we can't get directly from here because this triangle uses an angle of theta. It doesn't use an angle of 2 theta. I could tell you what sine of theta is, but I can't tell you what sine of 2 theta is right away. So in order to find out what sine of 2 theta is, There's that double angle identity again. This becomes 2 sine of theta cosine of theta, and each of these I can get from my triangle. According to my triangle, sine of theta would be opposite over hypotenuse, so x over square root of x squared plus 1. And cosine would be adjacent over hypotenuse, so 1 over square root of x squared plus 1. And if you multiply those two denominators together, the square root is going to get squared away. So this will just be x squared plus 1, and on the top we just get 2x times 1, which is 2x. So here's our answer. Okay, next one here. We want the sine of the inverse cosine of negative 2/3 plus the arc sine of 1/4. And I haven't really talked about this arc sine notation. Arc sine is another way of just writing inverse sine. It's kind of an older way of doing it. You don't see it that often, but just know that occasionally it might pop up, and all it means is inverse sine of 1/4. So arc sine and inverse sine mean exactly the same thing. So what are we trying to figure out here? Each of these inverse pieces is an angle, and I've got 2 of them. So let's call this alpha and this beta. So we're trying to find sine of alpha plus beta. And according to my sum formula for sine, this would be sine of the first times cosine of the second plus cosine of the first sine of the second. So I need to figure out what these 4 pieces are. And in order to do that, I'm going to need to draw some triangles. So let's go to our alpha first. We're going to let alpha be the inverse cosine of negative 2/3. So cosine of alpha is equal to negative 2/3. Right away, think about inverse cosine. It goes through quadrant 1 and quadrant 2 from 0 up to pi. So if this is a negative 2/3, then that means we're talking about quadrant 2. So let's draw our triangle. Here's alpha. Cosine is adjacent over hypotenuse. So 9 minus 4 is 5, so this will be root 5. And I want to know from this triangle sine of alpha and cosine of alpha. Well, sine of alpha would be opposite over hypotenuse, so root 5 over 3. Now remember what quadrant we're in. We're in quadrant 2. So sine is still positive in quadrant 2. So this is going to be plus. Cosine of alpha is adjacent over hypotenuse, so that's that 2/3, and in quadrant 2 cosine is negative. So that's everything that I need using that alpha. Now we're going to do everything we need using beta. So let's let beta be inverse sine of 1/4. So sine of beta equals 1/4. So if this is positive, and remember sine goes through quadrant 1 or quadrant 4, if this is a positive 1/4, then that means we're talking about quadrant 1. So let's draw our triangle. Here's beta. Sine is opposite over hypotenuse. 16 minus 1 is 15. So this is going to be square root of 15 down here. And I need to know cosine of beta and sine of beta. So according to this triangle, cosine is adjacent over hypotenuse, so square root of 15 over 4. And sine of beta is 1 over 4. And we're in quadrant 1 for both of these, so both of them are going to be positive. All right, we have all the pieces. Now all we have to do is go ahead and clean it up. So root 5 times square root of 15 is going to give me square root of 75, which will reduce. We'll do that in a moment. And then over here, we have a minus. 2 goes into 4 twice, and that'll give me a 1/6. Square root of 75 is a 25 times a 3, so this is 5 root 3. So we get 5 root 3 over 12 minus 1/6. And you can just leave it like that if you like. Okay, let's take a look at the next example here. Solve the equation 3 inverse sine of x equals to pi. So if we want to solve this for x, probably what we always like to do when we're solving is to isolate that x as much as we can. So the first thing that I would do is get rid of this 3, divide both sides by 3, and this is saying inverse sine of x is equal to pi over 3. So that means if we wanted to solve for x, we'd have to undo this inverse sign, and what undoes an inverse sign? A sine. So if we take the sine of both sides, we would get sine of pi over 3, and if you think about your unit circle, pi over 3 is right up here. The sine value is root 3 over 2. So that means x must be square root of 3 all over 2. Okay, the remaining 3 trigonometric functions also have inverses if we appropriately restrict their domains, but you're not going to be held responsible for remembering these. So you don't need to worry about inverse cosecant, inverse secant, and inverse cotangent. But you might be asked to find some values, and I'm just going to show you how you can do that using the 3 that we already know. And we're going to be using our calculator to help us out. So suppose I wanted to know what the inverse cotangent of 5 is. There's no cotangent button on your calculator, so there's no inverse cotangent button either. So the way to do this is to call this theta, and that means that cotangent of theta is supposed to equal to 5. Now what we need to do is rewrite this using one of the 3 trig functions that are on our calculator. And cotangent is the reciprocal of tangent, so that's the one I'm going to use. I'm going to change cotangent into 1 over tangent of theta. Then I'm going to cross multiply that tangent to the other side. And I'm going to divide by 5 to try and isolate that tangent by itself. So this is really asking for what angle theta, when you take the tangent of it, gives you 1/5. If I wanted to solve this for theta, I'd have to undo the tangent with an inverse tangent. And that we do have a calculator button for. So at this point, you could pull up your calculator and just do inverse tangent of 1/5, and this is in radians, so 0.197 radians. And you could always convert to degree mode if you needed it in degrees. So let's go ahead and do that. Whoops. If I change this to degrees, so if I just re-enter in that command again and hit enter, now this is giving it to me in degrees. So 11.3 degrees. Okay, so those would be your 2 choices for your angles. Now for inverse secant of -3, we're going to do the same thing. This is an angle, so let's call it theta. So secant of theta is supposed to equal -3. Convert secant into its reciprocal, cosine, 1 over cosine. And then multiply that cosine across to the other side, divide through by -3, so -1/3 equals cosine of theta, and then to get theta, you would just do inverse cosine of -1/3. And I'll leave it to you to type that into your calculator, but the 2 values that you'll get would be 1.91 radians, or 109.5 degrees. And remember, these angles that you're getting should be between 0 and pi radians or 0 and 180 degrees when you're talking about inverse cosines. For inverse tangents or inverse sines, they would be between -pi/2 and pi/2 for your radians, or -90 degrees and +90 degrees for your degree angle. Last one here, inverse cosecant of pi. If we call this theta, then this means that cosecant of theta is supposed to equal to pi. Convert this into your reciprocal function, which would be sine, so 1 over sine of theta is equal to pi. Multiply that sine of theta across, divide through by the pi, so 1 over pi is equal to sine of theta, and to undo the sign, we're going to use that inverse sine button, and you would type that into your calculator, and the two different values that you would get would be 0.324 radians or 18.56 degrees. Alright, that concludes our lecture on inverse trig functions. Please make sure that you memorize the restrictions on the domain and range for the inverse sine, inverse cosine, and inverse tangent functions. Good luck.